Okay, last class we started this discussion of polarization. We had just this one general brief discussion. Okay, then this lecture we are going to see how to produce a polarized light. Okay, there are many methods. Okay, there are many methods. Not that these are only two methods. Okay, there is also one method like polarization by scattering. Okay. When scattering happens, then also the scattered light is polarized. Okay, and several other methods are also there. But here we are going to discuss only these two. Okay. Polarization by a Polaroid, and by reflection. These are two most common and simplest methods to polarize a light. Okay, note down these things. Okay, of course I'm going to explain all of this diagram and all. Polaroids are, first of all, they are materials. Materials like I have glass, plastic, rubber and all that. So polarides are also a material, but a special type of material. Okay, are materials having long chain molecules like hydrocarbons, long hydrocarbons. Okay, or any like polymers. Okay, fiber type structure. Long chains. Okay, they are aligned in one direction. Okay, so I have this material, from that type of material I have made this one small let's say transparent disc like this, or a sheet made of such material. Okay, so it has this long chain of molecules, and all the molecules are aligned in one direction. Okay, and on this molecule the unpolarized light is incident. Okay, then what happens? When light falls on them, that means these molecules of this material, then electrons in molecule start moving along length. Okay, electrons, you see, this is not a metal. This is not a metal. Okay, the metals have free electrons. They can move everywhere and anywhere. Okay, here the electrons are constrained. They can move only along the molecules. It's a long chain molecule, all molecules are aligned in one direction. So electrons can move only along the molecule. So they start moving. Why do they move? Because there is electric field. In electromagnetic wave, there is electric field. So under the influence of that electric field, the electrons will start to move. They can move only along this chain, along this length of the molecule. Electrons are not free. They cannot go out of the molecule and then move. It's not a metal. Okay? Okay. Along the length of molecule because of electric field. As they move, they absorb energy. Okay, so they will absorb energy from the electromagnetic wave and they will start moving along this length. Now, when they absorb energy, then in this direction, okay, this is my unpolarized light. So electric field keeps on rotating. Okay, so I can find the component of electric field in any direction. Generally, we resolve a vector in two normal directions. Okay, so here what we are doing is, this is electric field. I am representing it by several vectors. Okay, all this electric field can be resolved in two components. One component is along this length. The other component will be normal to this length. Okay, so which component will be absorbed? The electrons are moving along the length of molecule. They are absorbing energy from the wave, EM wave. That is, the electric field is going to diminish. Okay. So they are absorbing which component they will absorb? They will absorb this component. Okay, this component is absorbed. This component here is absorbed. It is absorbed. It diminishes. It diminishes. Okay, and if it is a perfect polarization, it will become zero. Okay, but when the electrons absorb energy, this component, the component which is along the length of molecule, that component reduces. Okay, it is diminished. Okay, the other component, there is no effect on the other component. It remains almost same. Okay, the component normal to the chain remains almost same. Okay, so only that component is transmitted. Okay, so one component is absorbed, the other component E2 is transmitted. transmitted. Okay. So when light comes out, then electric field will be in one direction only, in one plane only. And what is that plane? That will be normal to this chain of molecules. Okay. So this line we are showing, this is the chain of molecule, and this line here is perpendicular to this chain. Okay. So all the electric field will be along this line only. The other component is getting absorbed. It diminishes. It is reduced. Okay. We say that light is polarized in direction perpendicular to length of molecule. Okay. We have symbol for this. This is the symbol. This is the symbol. Okay. So this line. So when I have this kind of symbol, this line shows us polarization axis. That means the outcoming light, the transmitted light, is going to be polarized along this direction. That means the component of electric field will be in this direction only. Okay? You understand this? You understand? Okay, now what will be effect on intensity? Because one component is getting absorbed. Okay? So let's say that intensity here is I naught. Okay? So I naught, unpolarized light. Okay, it is unpolarized light. Unpolarized light. Okay, intensity I naught is proportional to E naught square, amplitude square. Okay, I can write it like this: I naught is equal to some constant k times E naught square. Well, let's say it is. Okay, some constant. Now, this unpolarized light, the electric field vector keeps on changing. Okay, out of that, one component gets absorbed. One component gets absorbed. So every vector, all of these vector infinite directions, all of these vectors are going to have components. One component along the length, okay, length of molecule. The other component along this transmission line. So we are breaking all the vectors in two directions. Okay. Now what will be the intensity then? Okay, in polarized light. Polarized light. Okay. You see this theta keeps on changing. Theta will be different. Theta is going to be different. Okay. So this intensity I is equal to average of you see either sine component or cos component remains. I am breaking it in two parts, so I can call any one sine and cos. So either only one component will remain. One component is getting absorbed. Only one component will remain. I can say it cos component or sine component, does not matter. Okay. It will be average of k E naught square cos square theta. Let's say it is k E naught. So one component. So this E naught is going to have two components. Okay. E naught sine theta and E naught cos theta. Okay. The sine theta and cos theta will keep on changing. Okay. That's why we are finding this average value. Okay. This will be equal to k E naught square average of cos square theta. A standard result. Okay, we have been using this result for many times now. Okay, for first time we did it where, in which chapter? We actually derived the average value of cos square theta in AC, alternating current. Okay, from that point onward we have used it several times. Okay, so here also I am going to write the direct result. What is the average of sine square theta and cos square theta? Both are same. It is equal to half. Average of sine theta cos theta 0. Average of sine square theta cos square theta, or both are same, equal to half. Okay, so this becomes half times of k E naught square. It becomes I naught over 2. It becomes half. Intensity becomes half. Okay, so if this intensity is I naught, intensity here becomes I naught over 2. Okay, this is I naught here. This intensity becomes I naught over 2. Now this is something that you will remember. Something that you will remember. Okay, so when the unpolarized light, this is unpolarized light, when it is passed through a polarizer, intensity is going to become half. Directly half. 50% is absorbed, 50% transmitted. Okay, all right. Now, interesting thing. This is unpolarized light passed through a polarizer. This is also known as a polarizer. It is made of a Polaroid. Polaroid is the name of material. Polarizer. Intensity becomes half. What will happen if I pass this light, I pass a polarized light through a polarizer. Unpolarized light passed through polarizer. It becomes polarized. Intensity becomes half. You have to remember this. What will happen if I pass a polarized light through a polarizer? A polarized light through a polarizer. Okay? Let's see. Okay. It's like this. What we are going to do? Okay. We are going to see what happens when we pass a polarized light. We pass a polarized light through a polarizer. A polarized light through a polarizer. Okay, it's like this. Okay, let me draw this diagram here. I have this unpolarized light, let's say. Unpolarized light. Okay, it has certain intensity. Okay, we are not bothered. It is passed through a polarizer. Polarizer. Okay, this is a polarizer. This is its transmission axis. Transmission axis and polarization axis both are same. That means along this direction the light is going to be transmitted. It is going to be polarized in this direction, in this plane. Okay, let's say this is the direction along vertical. Let's say it is like this. Okay. Then what will happen? I will get light of some intensity. I get some light. Let's say that electric field, the amplitude of electric field here is E naught and intensity is I naught. Okay, do not be confused here. Here I am saying I naught. This is intensity of unpolarized light. Unpolarized. Now the light is already polarized. Okay, so this is going to have certain intensity. I don't bother. What it will be? By the way, it will be double of this. Double of this. Now this is a polarized light. This is a polarized light. I am passing it through another polarizer. This is another polarizer. This is another polarizer. Okay. This another polarizer makes some angle from this plate, from this axis here. Let's say that this is its transmission axis. This angle is theta. Okay. This angle is theta. Then what will happen? What will happen? I am going to. Okay, so very interesting things happen. Okay. Can you think what is going to happen? What is going to happen here? What is going to happen? Now, this field will have two components. This field is going to have, it is E naught, it is going to have two components. One component, okay, along this polarization axis. Okay, this is the polarization axis, and one component normal to it. Okay. This is E naught. This angle here, okay, this angle is theta. So this is going to be equal to, this component is going to be equal to E naught cos theta. Okay, and the other component here will be E naught sin theta. Makes sense? I am breaking this component. So what we are doing? First we are polarizing the light. First we are polarizing the light, and then we are passing that polarized light through another polarizer. Now the another polarizer, the angle between the plane of polarization of this light, incident light, it is polarized light, and the polarization axis of the other polarizer is theta. Okay, so what I am doing? I am breaking this electric field into two components along the polarization axis and normal to that. Now this is going to be transmitted. This is going to be absorbed. Okay, so in the final transmitted light, this is the final transmitted light. Okay, I am going to get electric field in this direction. This will be equal to E naught cos theta. Let's say that intensity is I. So first thing you have to understand what has happened. Amplitude has decreased, that's fine. Intensity has decreased, that's also fine. One other very interesting thing has happened. The plane of polarization has rotated. It has rotated, okay. This is a polarized light. This is a polarized light. Polarized. This is unpolarized. Okay. So this light, electric field is oscillating in one given plane. Let's say this is the plane. In this plane it is vibrating. Now when I pass it through another polarizer, now the plane is going to change. It is going to change. So we are changing the plane of polarized light. That is first effect, very important effect. And then the intensity is also going to reduce. Okay, what is the intensity? I naught is equal to K times of E naught square. I is equal to K times of E naught cos theta square. This becomes K E square and then cos square theta. Okay. What it becomes? I is equal to I naught cos square theta. Okay. What is theta? Theta will be the angle between the plane of polarization of the light, incident light, and the polarization axis of the polarizer. Okay. So whenever we make such type of arrangement, okay. So the first polaroid is known as a polarizer, and this is known as an analyzer. Now, what will be intensity if theta is 90? Okay. If theta is 90, okay, I is going to be 0. Okay. If theta is 0, I is going to be I naught. Okay. Interesting thing. Okay, how interesting it is. Let's try to understand it this way. Some light is coming. I want to find out whether it is polarized or not. A very interesting application of this. I am here standing in this room, full of light. Light is coming into my eyes. I want to find if it is polarized or not. My eyes cannot do it. Okay, our brain, our eyes cannot differentiate between the polarized and unpolarized light. Okay, but if I have a polarizer, it's very common thing. Nowadays, many sunglasses are made of polarized materials, polarizers. Okay, so you take one of those glasses, or you take a polarizer. Okay, keep it in front of your eyes. Keep it in front of your eyes, and you rotate it. Rotate it. Now rotate it. If the light is unpolarized, then intensity will not change because it is always going to be I naught by 2. It is always going to be half of that I naught by 2. So whatever is the light intensity, when I use this polarizer, it is going to become half. That's it. Now, but if the light is polarized, in that case, when I rotate it, intensity changes. It changes from 0 to maximum. Okay. When it is 90 degree, then no light it will become dark for me. I cannot see anything. Okay. When it is 90 degree. Okay. So as I rotate it, the intensity keeps on changing. Then I know that the light is polarized. Okay. Okay. So that's it. A very simple topic. That's it. You just try to remember this. Okay. This is given a name. This actually is given a name. This is Malus law. Malus law. A very simple law, Malus law. Okay, so understand this. Unpolarized light passed through a polarizer becomes half. Intensity becomes half. Okay, polarized light of intensity I naught passed through a polarizer. Intensity I naught cos square theta. Theta is the angle between this plane of polarization and this transmission axis, polarization axis. Okay. First effect, intensity changes. Second effect, the plane of polarization itself rotates. Okay, it rotates. Okay, that's it. Let's do few problems. And then we'll move on to the second thing, that is reflection. Polarization by reflection. Polarization by reflection. After this, okay, let's do few problems. Unpolarized light, unpolarized light of intensity I naught is incident on a set of polarizers as shown. Okay, polarizers as shown. What is intensity of final transmitted light? Okay, so I have this set of polarizers, final transmitted light. Okay, can you read it clearly? Okay, I hope that you can read it clearly. Okay, so it's like this. First, unpolarized light of intensity I, the incident light. Okay, so here we have this set of polarizers. I have this first polarizer here. Okay, first polarizer, and then I have this second polarizer. Okay, let me draw a smaller diagram. It will take too much space. First one, I have this thing here. I have one polarizer here. This is the transmission axis or polarization axis, and this is my unpolarized light. Okay, this is unpolarized light, intensity I naught. Okay. It is incident here, first polarizer. Now I have one more polarizer here. Two polarizers. Polarization axis of both are in the same direction. So light will pass through this first, then through this. What is the final intensity? Okay. Now second is like this. I have this first polarizer. Okay, this is my light. This is I naught. Okay. This is the polarization axis or transmission axis. Okay, both are same. And then I have this thing here. Okay. Now this is the axis here. Now here it is. This angle here is 30 degree. The angle here, this angle is 30 degree. Okay. Now third, let's do this. Okay, start doing the, note down the problems. We have to do all of them. This is my unpolarized light. Okay, unpolarized I naught. It is incident. This is the first polarizer. Okay, this is the transmission axis. Now this is the second polarizer. Okay, this angle here, the angle here is 60 degree. 60 degree. Okay, and then one other here. Okay, this is the, okay, this angle here. Okay, this angle here, this angle is 90 degree. 90 degree. Okay, what do you think? What is going to be the final light in all the cases? It is 60 degree. 60. Okay. What do you think? What is going to be the answer? All three problems. Okay, noted, solved all of this. Okay, let's see. After passing through first polarizer, it becomes polarized. It becomes polarized. What is intensity? I naught over 2. Now, what is angle between this and this? Okay, I have this Malus law. Malus law here. Okay, so I is equal to I naught cos square theta. This I naught is intensity of polarized light, not unpolarized, polarized light. Okay, so what will be the angle here? This theta will be 0 degree. Okay, so this I will be equal to I naught over 2. Okay, so in place of I naught, I will write this value and cos square 0. Cos square 0 degree. Okay, this becomes I naught over 2. Transmission axis and this plane of polarization, both are in the same direction. Okay, so there is no change. All of the light is transmitted. Now here, this is my polarized light. It becomes I naught over 2. Now in this case, the angle here theta is 30 degree. Theta is 30 degree. Okay, the angle between this line here, this line and this line. Okay, 30 degree. So what will be I? I will be equal to I naught over 2 and cos square 30. This becomes 3 I naught over 8. Okay, did you get the same answer? And here, very simple topic. This becomes I naught over 2. Okay, here, what is theta here? Here theta is, you see, I have to find this angle. So the theta is not 60, but theta is 30. Theta is 30. Okay. Here I is going to be equal to I naught over 2 cos square 30. Okay. This becomes 3 I naught over 8. Okay. So and this becomes the plane of polarization. The plane of polarization has rotated. Okay. The plane of polarization has now rotated. It will be along this the axis of this polarizer. It has rotated by what degree? 30 degree. Now what will be angle between this and this? Okay. So from this line, you see, from this line, this vector here, this field here, it makes what angle? 30 degree. It makes 30 degree. Okay. From the same line, this direction, it makes 90 degree. Okay, this could be little confusing. It's no big deal. Simple mathematics, not even mathematics. Simple thing. Okay. So from this line, this makes 30 degree. This makes 30 degree, and this makes 90. Okay. So what will be angle between this and this? It will be 60. Okay. The theta here will be 60. Okay. So this final light will be equal to 3 I naught over 8. Okay. Cos square 60. So it becomes 1 over 4. So 3 I naught over 32. Okay, that's how we do it. Okay, you got the same answer. You also got the same answer. So that's it. Okay, in problem sheet you will find few other problems. Okay, topic is not so difficult. You can do it very comfortably. Now the next one. Polarization by reflection. Polarization by reflection. Polarization by reflection. Okay, so let me clean all this. Okay, let me write it here again. Polarization by reflection. Okay, there is some theory. Let me write it down. You also note down. Okay, when light is reflected from an interface separating two mediums, then reflected light is polarized. First of all, this is observation. This is what has been observed. It happens all the time. Reflected light is always polarized. Always. So whenever light reflects from, of course the light is going to reflect only when the medium changes and it is reflected from an interface, okay? So whenever light reflects, the reflected light is always polarized. Okay, now let's see, there are some conditions. Okay, the degree of polarization depends on angle of incidence. Angle of incidence. Okay. Now, if angle of incidence is 0, okay, that is normal incidence. That is normal incidence. Okay, if angle of incidence is 0, then there is no polarization. Okay, then there is no polarization. Okay, remember, you have to remember these things. Okay, no big, not very complicated theory. The theory as such, the statements as such are very simple. Now, why it happens, understanding that requires a lot of other concepts, but we are not going to do that. Okay, fortunately, that is part of very advanced courses. Okay, very advanced. Why that happens? Okay. Now, we are not bothered about that. What happens? That's what I want to know. Okay, with only that we are concerned. What happens? Why it happens? That requires a lot of other concepts. Okay, very complicated. Degree of polarization depends on angle of incidence. That's it. Now, for one particular angle of incidence, okay, for one particular angle of incidence, okay, called Brewster's angle. Brewster's angle. Let me say this theta b. Very important. Okay. For one particular angle of incidence, okay, first of all, the degree of polarization, how much polarization will happen, whether it will be nil or complete or 60%, 40%, whatever it is, okay, that will depend on angle of incidence. First thing to remember. If angle of incidence is 0, there is no polarization. 0 angle of incidence means normal incidence, no polarization. For one particular value, okay, for one particular angle of incidence, which is known as Brewster's angle, okay, for one particular angle of incidence, reflected light is completely polarized. Completely polarized. Okay. So the angle of incidence for which the reflected light is completely, totally polarized, that angle is known as Brewster's angle. Okay. And when that happens, then reflected and transmitted means refracted, and when that happens, then reflected and transmitted light are perpendicular to each other. Okay, now it's like this. I have this medium mu1 and this medium mu2. Okay, light is incident like this. Let's say this is the incidence, light of light. Okay. Now this light is unpolarized. Okay. The plane of oscillation keeps on changing. Now I can break all those directions in two directions. One will be along this plane, in this plane of this diagram, in the plane of reflection, okay, and normal to that. So we are representing this by a dot here, dot symbol, dot. Okay, you understand the meaning of dot? So we are breaking all the electric field, everything. Okay, electric field keeps on changing direction. I am breaking everything, all the vectors in two directions. One is along this plane and the other is normal to this. I can always break a vector into perpendicular directions. Okay, here I am doing it. Okay, so this component here from the arrow, by the arrow, it is in the plane, and by this dot here, it will be normal to the plane. Normal to the plane. Now, the reflected light here is going to be partially polarized. It is partially polarized. Partially polarized. Okay. For one particular angle, it is completely polarized. There is Brewster's angle. For this angle, there is no polarization. That means some other angles, for intermediate angles, it is going to be partially polarized. What is the meaning of that? That means one of the components is going to be absorbed. Partially, not completely. Which component is absorbed? The component which is parallel to this plane. Note it down. The component parallel to the plane is absorbed. Parallel to this plane, parallel to the plane of the plane of incidence. That's it. Plane of incidence. Plane of reflection. Okay, the component parallel to the plane of reflection the component in the plane of reflection gets absorbed. Okay, so that means this is going to decrease a little bit. The other component will remain. Okay, and this is going to decrease a little bit here. Okay, so this component is getting absorbed. This component does not change. That means this is partially polarized. Okay. What about reflected light? This is the reflected light. Okay. Here also there will be partial polarization. Partial polarization. Okay. So sometimes this question is asked that reflected light is polarized. What about the transmitted light, the refracted light? This also is partially polarized because the component in the plane is going to be absorbed for here as well as here in both cases. Okay. Now this also is partially polarized. Partially polarized. Okay. Makes sense? Now, at one particular angle of incidence, this angle, for Brewster's angle, this is going to be completely polarized. Okay. So how it will appear? So this is okay. So one such angle is here. Now this will be my reflected light. Reflected light. Okay. And this is my transmitted light. Okay. So for one fixed angle, this is equal to theta b. We call this Brewster's angle. Okay. For this angle, let's look at the polarization. This is my incident light. Incident light. It has both components in the plane and normal to the plane. Okay. Here I have both components in the plane and normal to the plane. Now this light is completely polarized. That means which component will remain? Only this component, normal to the plane. Only this component will remain. The other component in the plane of reflection, that is completely absorbed. So I am left with only this. That's it. Okay. This is complete polarization. Completely polarized. Completely polarized. This is mu 1. This is mu 2. This is partially polarized. It is never completely polarized. The transmitted light is partially polarized. Okay. I am writing this again. Partially polarized. Okay. So this will also be Brewster's angle, theta p. Okay. Now after that, and when that happens, when what happens, when that happens, this thing happens, okay, then reflected and transmitted light are normal to each other. That means this angle here is 90 degree. This is 90 degree. Okay, that's it. This is known as polarization by reflection. Now if I ask you, what will be Brewster's angle for these two mediums, mu1 and mu2? Let's say I give you air and water. What will be Brewster's angle for air and water? Glass and water. For any medium, mu1, mu2. What will be Brewster's angle? Can you find out? Okay, try to find it. It's very simple. Very simple. Okay. Very simple. How do we do this? Okay. We write like this. Mu1, Snell's law. Snell's law. Okay. Mu1 sin theta 1 is mu2 sin theta. Okay. So this becomes mu1 sin theta b. This is angle of incidence, Brewster's angle. The whole thing is 90. Then what will be this angle here? This angle. Look at this line, this normal. Normal is 180. This whole angle is 180. Out of that, this is 90. That means these two are 90. Okay. So this becomes 90 minus theta b. Okay. So I will write it like this. Is equal to mu2 sin 90 minus theta b. What do I get? Mu1 sin theta b is mu2 cos theta b. Okay. I get tan theta b. Mu2 over mu. That's it. This will be Brewster's angle. And let's conclude. Okay, the chapter is complete.